Welcome to another session of EPG Pathshala covering architectural attention to high-rise buildings. The topic that we are going to look at in this few minutes that we have in front of us is data center air conditioning. Over the past few years, one has noticed the amount of reliance one has started placing on computers. These computers today have become a device in one's working environment which one cannot do without, and reliance is increasing more and more. There was a time when a few decades back having a street lamp controlled by a timer used to be an ultimate in automation. Adding a lux meter to the timer was considered a big step in automation. Today these devices are merely small sensors which one plays for, and you go beyond, far beyond all these, and not only go beyond in sensing but learn how to integrate them to effect energy economy, to effect lifestyle changes. Today, for instance, one can have a house and every parameter in the house, starting from the curtains, can be controlled by the person operating from his office a few kilometers away. For instance, the curtains which face west, he can automatically arrange for these western curtains to be closed, let us say at 2 o'clock in the evening, and open up at say 6 o'clock in the evening. Automatic devices, timer controlled, or with overrides from his own office, from his own maybe cell phone. Now all this is done with the help of data, use of this data, and most of this equipment gets to be housed in data centers. So virtually today one cannot imagine a high-rise building having, even if it has a single user, it definitely needs a proper data center which, if not anything, starts collecting biometric data for salary payment and virtually every other device which one goes by. Once you look at a data center, the topic related to data center and its air conditioning would mean how is it different from a common air conditioned space, meaning let us say an office. Today virtually all offices, high-rise buildings are air conditioned for the sake of comfort. Now within that we have seen that you need a small place called the data center. Now how is this data center different from the normal air conditioned space? Can you just cordon off a small area in your office space and say, look, this is my communication equipment, this is my data center? Perhaps not. And if you cannot do such a thing, why is it that it cannot be done? It is basically because data centers today house equipment which is far more than in any other office. Like for instance, the categorizing of this equipment would lead to saying that a data center first and foremost needs equipment which will communicate. It will need equipment which processes this communicated data. That means it needs servers, it needs a storage system, and to keep both these in operation there will perhaps be an input-output man who will be working with a workstation, and after all this data is processed, for posterity to come you might require a storage system which will be dead, but still dead storage in the sense of storage, but still alive for you to be able to access it at your fingertips. So largely these equipment will be housed inside, and none of these equipment run without guzzling tremendous amounts of power. If one were to go back, let us say 2 decades back, 25 years back, when equipment started coming into the market and getting attention from people, communication equipment barely consumed 500 watts per square meters. That was the kind of loading, power loading that required. Servers consumed a good 300. Workstations, if they were there, would perhaps intermittently consume 120 watts per square meter as long as they were occupied. The tape storage system would be continuously on, as you will see, because it does very little active work, its power consumption is a little on the lower side. Basically items 1, 2 and 4 are equipment which is on all the time. workstation is on as long as the input output person or service personnel are in the area. So basically this was the kind of loading that was envisaged a few years back, a long time back, when the equipment came into vogue. Today the equipment loading has climbed far beyond those levels, and 2000 watts per square meter is perhaps a good figure to be guessed. You could still be wrong, and the data center that you are planning for might be much higher than even this figure, but as a guess one can definitely start with a figure of 2000 watts per square meter is the load. Now if this is the kind of load that is imposed, it would mean that you will need a separate type of air conditioning equipment for this area. Now the load is one aspect of the equipment of the AC design, you might say. Apart from the load, different computers unfortunately require different conditions to be maintained. In its infancy, the computers were perhaps made largely in Europe and in the upper reaches of America, where the climates were very low temperature, and quite naturally all these hardware which went into making these equipment insisted upon the computer to be maintained at a very low temperature. 18 degrees centigrade was perhaps the high point. They wanted temperatures even lower. That was when the market was entirely taken by IBM computers, ICL computers. Later on, slowly, as components started getting tropicalized, as components started coming from all over the world, people realized that there was too much of an impact on air conditioning, and today the computers are rated average on conditions like this. That means the temperature, they say, can be 15 to 32, which means you can use it in a high latitude area and somewhere in the tropics with comfort air conditioning. Likewise, the RH has been given a wide band. Now there is no point in trying to distinguish an air conditioning system with such high wide bandwidth of RH control and temperature control. So if you are faced with this kind of input from the manufacturer of air conditioning equipment, a good designer would perhaps look for a temperature like this, which is within this range but for a smaller bandwidth. This would be uncomfortable for people. So in the room you look for a temperature of 20 to 25, which means the set point is around 22 plus or minus 2 degrees. Likewise, the set point for RH will be something like 50 plus or minus 5%. Now these conditions which you select for your room are well within what the manufacturer wants, but they have been selected at the high end of the spectrum that was desired, so that you do not spend too much money on your air conditioning equipment. So in other words, with the type of data that you collect, you freeze it onto a requirement, and after that requirement you find that when an office requires something like 150 square feet per ton of air conditioning, your computer center will call for 20 square feet per ton. In other words, it is minimum 5 to 6 times more. Here you would find it is about 8 times more than the office air conditioning. Now it is not sufficient to say that you need 8 times more. In other words, let us say you had a very small room which required a 2-ton air conditioner. Now after you put in your server room inside that, it might require 16 tons of air conditioning. Now it does not mean that 2 tons has to be augmented by another 14 and you get 16 tons, because a good air conditioning man will tell you that air conditioning cannot be bought by the ton. What has to be looked at is the air quantity of that machine. Now in this kind of a loading, you would see that it is all basically sensible load. In other words, there is no moisture, it is all dry heat equipment, which does not contribute. For instance, now supposing you are doing an auditorium, you will find that there are people, you will find that you have to add fresh air. Now these two parameters add a tremendous amount of latent load, whereas in a computer room or a server room, data center, you will find that there is virtually no latent load. In fact, good computer rooms very rarely, except for 1 or 2 input output people, you find that they are not occupied. So in such a scenario, it is only the dry heat which comes, it is only the sensible heat which comes, and the effect of this on the air conditioning is that you need a larger air quantity. In the place where you had a latent load, one would say that you need a smaller air quantity per ton, whereas here you will need a larger air quantity. The larger air quantity can be as large. In a normal air conditioner, if you take your catalog, you will find that your room air conditioner at home, for every ton of air conditioning it gives out 400 CFM per ton, whereas a data center air conditioner will give out something like 700 to 900 CFM per ton. So, in other words, it is not only having larger capacity, it is having a different type of air conditioning equipment which is called for. What is the impact? This part of it, different equipment, different CFM, once you are aware of it, you will perhaps leave it to an air conditioning specialist to be able to source the equipment for you. But on the architectural front, what is the interface of this big equipment onto the server room? Basically, with a larger CFM per ton, the equipment becomes larger. So, in other words, what is it that will be required? You will need a large AHU room to be able to cool and house the data center, house the air conditioning equipment of the data center. You will need a room of this size, 4 meters by 3 meters, for every 20 tons of cooling. So, for instance, if you have 60 tons of cooling, you will need correspondingly this bigger room. If you have a bigger tonnage, you will need this kind of a room. So, these are as a thumb rule for a designer to be able to plan for AHU rooms that are required for data centers. In other words, the moment you have a good data center, ideally it should have an AHU room next to it. The moment you put an AHU room next to your data center, what are you having? You need air conditioning to be transmitted from your AHU room into the data center, and hot air from the data center to be pulled back into the AHU room to be able to recycle that air and reuse it, so that you effect economy in the cooling load. Now, this is what it would look like. In other words, if the data center in floor plan, this is a sectional view, you would have this much as the data center, you need this much as your AHU room. In most of the data centers, you find that the rate of obsolescence on the equipment is so large that you can never get a formal equipment layout in the data center. It is not uncommon to find a specialist, a data center specialist, who will tell you, look, give me a flat space, I will put my equipment wherever I like. I do not know what will be its shape earlier, later on. Today I can tell you this is it, but perhaps even by the time we finish construction of the room, we will find that that equipment does not fit. So, the interface between the two has happened to the extent that today most data center equipment gets housed in racks. These racks are approximately, you might say, about 0.9 by 0.9 meters. They look like huge cupboards which are about 2.1 to 2.2 meters in height and have a footprint of 0.9 meter by 0.9 meter. The front and the back are both openable and perforated for air movement and providing access. So, in other words, you are looking at a data center which will house equipment in racks with front and back openable, and these racks could be placed anywhere. So, in other words, what happens is, to develop a flexible system, people use what is called a UFD, underfloor air distribution system. So, the air conditioning equipment, instead of blowing on the top, tends to blow into a floor void. Now, to make sure that this, which is a less expensive area, less expensive equipment, but with a larger fire risk, does not communicate any fire in the case of a damage, you have a fire damper here. So, supply air is fed into this continuously, and air which has been used by the data center, the hotter air, is collected over the false ceiling and brought back in here for recirculation. Very rarely a small quantity of fresh air is added here, because there is nobody here who needs fresh air. It is enough to say that infiltration exfiltration provides for fresh air, or as a theoretical exercise one may provide for a very small quantity of fresh air to be added into the return air before it goes into the machine and it is recycled this way. From a designer's point of view, from an architectural designer's point of view, it is interesting to note that for such a large volume, the usable volume is only this much. If you really calculate by cubic meter, you will find that perhaps the data center occupies maybe 1/2 or even less of the total, because this is handling CFM at about 700 CFM per ton. Corresponding to that, you need a big void here. This false floor in normal cases would have been just a maybe 200 mm off the floor, but thanks to air having to be passed, it might become 1.2 meters off the floor. Likewise, for this large quantity of air to be able to go back, you might need under 1.2 void here. So, in other words, if this were categorized at, let us say, 2400 mm, which is the minimum, you might land up with this at minimum 25% and this at minimum 25% of that, provided there are no beams. If there is a beam, that will be a penalty which the structural engineer would demand. So, in other words, when you are looking at a data center from an architectural perspective, this is one aspect that one should bear, that spatial requirements are far more than one beam. If you go in and you see, oh, this much, but then unknown to you this is also there, unknown to you this is also there, and for it to be processed this is also there. So, you have a large requirement of air which is now put into this, and this floor has the normal 600 mm by 600 floor tiles. So, in other words, if somebody were to plunk equipment here, he could just remove the tiles of one equipment, put in a grill here, and you would have a grill here. Let us say this equipment gets relocated here. You close the earlier tile, open up the new tile, and you have a shifted pattern of air conditioning without having to do any mechanical work on your air conditioning equipment. So, in other words, to create that room that we saw earlier, the prerequisite was you need to have a fire separation, which is what we saw with the dampers. The volume of the service space is much more than that of the data. Service space meaning supply air, return air, and plant room space, that hatched portion that we saw in the earlier slide. In the AHU room, what you saw there was having only one air handling unit. It is definitely required to say that a server room will work 24/7 and 365 days in a year. Now, that is possible for that kind of equipment which has been built for that kind of reliability. Air conditioning equipment is not half as reliable as that, but given the best type of equipment that one can go in for, it is definitely necessary to consider that you have standby equipment on your air conditioning. Supposing your total load is met by 4 units, it is necessary to have a 5th unit as a standby, so that in probability if one unit fails, the standby unit can take over its job. Now, when we looked at a scenario where equipment placement could be very unpredictable, we tried to add an interface between saying unpredictable, yes, but a certain amount of order has been infused in it. In other words, these are the kind of racks that one would find. You would find that racks 0.9 by 0.9 by about 2.1 being set for any equipment. Some of these racks can operate and house something like about 60 servers. Now, a server can be something like what you see on your own laptop, less than an inch high. So, 60 servers would mean each server is stacked one on top of the other. In other words, you find something like 60 laptops being keeping here, and the heat from all those 60 laptops is liberated within this. Now, as we looked at in the earlier slide, one could open up a small amount of space here for supply air to come from the underfloor device and get into this rack, and hot air could get out. If it gets out over the false ceiling. I hope it is easy to correlate what we saw with the simple cross section onto this complex section. Here you see a row of racks facing another row of racks. This shaded portion is basically the front of the rack, and here you have the front of a second set of racks. So, this aisle space is called the front aisle. So, onto this aisle you have the front of this equipment, front of this equipment. The next set of equipment goes here. Again, front and front is here, the back and back is there. This is generally used for servicing of the equipment from the back. In most cases, this aisle and this aisle are the same size. This has a door in the front and a door at the back. So, in other words, one can decide upon having the front aisle of every machine as the cold aisle. So, that is the air where supply air is allowed. It can come from the top, it can come from the bottom, but this will become the cold aisle. The next cold aisle will be here. In between there will be an aisle which is meant for the service of racks, that will be called and categorized as the hot aisle. So, in other words, you have a system, you have added a sort of a system to something which was not categorizable. To a data man, he will come and tell you, look, I will keep 60 servers one on top of the other, but you told him, look, I want to have a detail whereby I should be able to provide for the services. These things will require power, they will require input data, they will require output data. So, ultimately as an interface between the services requirement and the process requirement, you have created a bund, you might say, an envelope, you might say. So, you have multiple envelopes lined up in an orderly fashion, so that fronts are available for the technician who operates on the electronic equipment, somebody who operates on the hardware will work in this, and it is assumed that this can be a little warmer than this. So, this is called the cold aisle, this is called the hot aisle, this is called the cold aisle, this is called the cold aisle. Now, this is a typical layout of data center room. People like ASHRAE, the American Society of Heating, Refrigeration, Air Conditioning Engineers, have invested millions of dollars in finally coming to this kind of a thing as a recommended device for layouts, and I am happy to say that very rarely you will see a contradiction from this. People today have sort of straitjacketed themselves to accept that all servers, whatever be the type, whatever be the type of wattage they consume, will be marshaled into this equipment. So that once it is there, all the services people, including the air conditioning man, including the electrical man, including the data man meaning let us say even a simple thing like a telephone call. The telephone technician now knows that okay, this is the place where I need the terminations of my cable trunks. So, you have a false floor underneath, you have a false ceiling on top, and you are able to, all the services required for that equipment can be reached. What you saw in the earlier thing was an isometric view. You saw that there were cold aisles and hot aisles, and you will, as I showed you in the earlier device, this is the cold aisle, this is the front of the machine, this is the front of the machine. So, this becomes the cold aisle, this becomes the back of the machine, and the back of the machine, this becomes the hot aisle. So, this is again the cold aisle. Now, because these devices are factory made and in speed, you will find that invariably the false floor or the false ceiling is a 600 by 600 grid. So, what you see here is a 600 by 600 grid on the floor. In other words, from the center of a cold aisle to the center of another cold aisle, generally you will find that there are 7 tiles. In other words, it is 4.2 meters, 7 into 0.6. If you notice here, it is 1, 2, 3, 4, 5, 6, 7. So, there are 7 tiles which separate one cold aisle from the other. So, this is another standardization which has been achieved in a world of chaos as it started from equipment placement earlier. So, what you saw in a psychrometric view, in an isometric view, you will now see here in terms of plan, and this is called a 7 aisle pitch with cold aisles and hot aisles. The supply air is put in on the front side of the rack, the return air is collected on the back side of the rack, and the return air goes virtually, because it is hot, it rises into a grill in the false ceiling, and the supply air comes from a grill on the floor. This grill is made sturdy enough to be able to allow people to walk on it without any fear of instability. This is a view of that same 7 tile arrangement which was earlier shown in isometric and plan. You will have a false floor where you will have cold air. This is the grill. One of the 600 by 600 tiles is just physically removed, and you put in a device which allows cold air to rush out here. So, technically the cold air goes here, but invariably most of the racks have perforated fronts and backs, as I mentioned, and to help air to move into this, because this was its earlier decided movement, now it moves into this and it gets out from here, it gets out through a return air grill in the hot air space. So, this fan and this fan help to push out the hot air from here. Whatever cannot escape through the fan escapes into the hot air, and this is the master collector from where you have 1, 2 and 3 hot points collecting into this and getting into this for being recycled into the machine and coming into this area. Now, this is as far as the standard racks that you will see concerned. I still said that this is a world of development, and it is not unusual to find that you design a data center with 2000 watts per square meter, and 3 years later down the line you are called back to say, look, my wattage has increased to 3000, I still need more cooling for this space, but I will not give you additional floor space. So, what do you do at that point of time? So, at that point of time, the air conditioning man will give you specials, which ideally would be to comply and give a bigger AH room, but having said that, it is a device which is very difficult to put, because these are housed in the middle of populated spaces, in the middle of populated office, and very rarely space can be allocated from department to department. So where you have very high density, which might be imposed as an expansion, or it might come in at the initial stage itself, it is possible to use devices which have water cooled doors. That means the rack which was imposed earlier is now made special, and cold water is put into these racks. So the cold water takes off a part of the heat directly. This is what you see here. Now this is a rack which you saw earlier. It has a door. This door will not only have side perforations, but by itself it is something like a eutectic pad. In other words, it is a device which is like a refrigerator door, thick and solid, but it admits cold water to go inside the thing. This cold water keeps this panel very cold, and this draws out the return water. That means water can be injected at, let us say, about 12 degrees centigrade. It goes in and returns at about 18 degrees centigrade. Now water is a very good media for heat transfer. So the pads or the servers which are here will transmit part of the heat to the air, but a larger quantity by radiation onto this cold surface which is close by, and you will have heat being transferred to the water. So in other words, the increase is not on the air of the air conditioning, but it has been short circuited and taken away by water directly, with pipelines being laid under the floor. Another type of constraint that can develop onto design would be that after you form these cold and hot tails, you might land up with specialist equipment, specialist requirements like this. For instance, all the equipment today is data protected, it is password protected. So technically you can have within the same rack equipment for two different customers here, but very few people are computer savvy, and most customers who pay for their data protection are generally very paranoid about security. They will insist that you give them a grillage exclusively for their servers. So this is a small requirement which tends to complicate what we earlier talked about, saying that equipment has become straitjacketed, everything is in racks. But should these devices become necessary, then you have different type of problem which will need solution by purely architectural thinking. Like for instance, now supposing you have a multi-story building with one tenant per floor and a common data center. Let us say it's a 10-floor building. That means you might land up with 10 tenants, and each of them, if he wants a separate enclosure which he wants to put a garbage lock and feel happy that he carries a key to it, then your geometry of the curve room will change. You will have to devise and improvise systems to suit this kind of odd requirement. Suffice it to say that it is not necessary, but having said that, it is also there that very few people will accept password protected devices if they are not very computer savvy. They will come around and say, no, something will happen, give me a lock, I want to keep it under my pillow when I go to sleep. You still do get such people. Having said that, there are a few small devices which have become very necessary because the amount of data and the equipment that you protect is very high. These are things like temperature alarms, very common. You just put in a sensor, if it exceeds for some reason, the alarm comes on asking you to put on standby equipment or ask you to shut down some of the servers. Moisture alarms, that means should the water from the AC equipment leak, you have moisture alarms. Then you have fire alarms. These are of course I think very common and very necessary, and very rarely precise temperature and RH controls, because today equipment, as I said, has a very large control width from 15 to 25. So precision is never required, plus or minus 2 degrees is good enough. Thank you.